This meeting is being recorded.
Welcome to Brandeis Mathematical Biology Seminar. Today we have Aaron Fogelson from the University of Utah. Thank you, Aaron.
Hi, thank you for the invitation. Someday I'll visit in person. I've never been to Brandeis, but for now, it's nice to see you guys. So I'm going to tell you two stories from our many projects on trying to understand how blood clotting works, or in this case, how it doesn't work. And so as I said, the talk has two parts, very different. The first part of the talk is joint work with physician and bioengineer David Koo at Georgia Tech, and with mathematician Jen Du, who's at Florida Institute of Technology and was supported by NSF. The second part is joint work with a whole bunch of people, mathematicians Karen Liederman and Suzanne Cindy, bioengineer Keith Neves, biochemist, I guess, Mac Monroe, and Katie Link, Michael Staub, and Kenji Miyazawa, who are all PhD students of one or the other of the people in this project. And that has been supported by National Heart, Lung, and Blood Institute. So, blood courses through our veins and arteries. Pumped by the heart, it's under pressure, which means there's a pressure difference between inside the vessel and outside. So a cut in the vessel, a hole in the vessel allows for rapid outflow of blood, and unless something stops it. And that's what the clotting system is for. It's the first responder for vessel injury. Okay, so I want to give you an overview of the whole process, very simplified version of it, but still useful. Can you see my cursor? Okay, in the upper left is the situation in the healthy blood vessel. All of our blood vessels, from the smallest to the largest, have a monolayer lining of endothelial cells, the green guys here. Okay, so in the blood, among many other things, are platelets, type of very small blood cell, and a whole host of proteins that are involved in different aspects of the clotting response. Prominent among them for the first part of the talk is fibrinogen and some VWF, von Willebrand factor, but I'm not going to say that repeatedly. Okay, the platelets, as they circulate, they're covered with receptors, and they're monitoring their environment. Okay? They get signals from the endothelial cells through substances released by the endothelial cells, tell them that things are okay. Okay? When they get those signals, they remain in a resting state. Wow, Danny Ruberman. I haven't seen him since Wesleyan.
Yeah, so yeah, hi Aaron, nice to see you.
Hi.
No, one event coming to Brandeis.
You were classmates?
Yes. Yeah, same year,
Oh,
1977.
Yes.
If you can,
Yes, long time ago.
I'm not sure if anybody else here was born then, but
I'm sure not, from the looks of the audience. Maybe even some of their parents were barely born.
No, let's not go that far.
Okay, so I was just trying to give an overview of blood clotting, and the situation in the top left is in a healthy blood vessel, blood platelets, these pink guys are surveilling the state of the vessel. They're talking to the endothelial cells, which are green, and the endothelial cells, when they're intact and happy, I call them healthy and happy endothelial cells, are telling the platelets, things are good, stay quiet. Then something could happen. It could be an over injury, or it could be that there's some inflammation or something else that disturbs the endothelial cells in some region of the vessel. Okay, so I'm imagining here that a patch of endothelial cells have been removed. That exposes material below the endothelial cells that's not normally in contact with the blood. And different things that are exposed trigger different parts of the clotting response. One thing that's exposed triggers platelets to adhere and to activate. And I'll tell you what activation means over the next little bit. Okay, and those I'm indicating with red platelets. One of the things that activation causes the platelet to do is to release various chemicals out into the blood plasma, tended to be represented by this blue cloud. And other platelets that see a sufficiently high concentration of one of those chemicals can also be activated, even if they don't directly contact the damaged wall. The second thing that that activation allows is for the platelet to become able to bind to other platelets. It's a very specific kind of adhesion. It involves receptors on the two platelet surfaces that have to be activated and bridging molecules between the surfaces, one of which is fibrinogen. Okay, so that allows a platelet clump or a platelet aggregate to build up. And if there's actually a hole in the vessel, that can result in a platelet plug. It can loosely fill the hole. As long as it remains intact, it can stop red blood cells from leaking out. It's probably not impermeable enough to stop plasma from going out. Okay, so that's one part, platelet aggregation. A second molecule that's exposed upon injury triggers another part of clotting called coagulation. It's a series of enzymatic reactions, which I will describe at length later. The end result is an enzyme called thrombin. Thrombin is the key player in a lot of clotting. It activates, well, it has lots of feedback, which I'll tell you about later. But for now, the primary thing we need to focus on is it does something to this fibrinogen molecule, which is already acting as a bridge between platelets. It cuts off a little part of the fibrinogen, and the resulting fibrin monomers spontaneously polymerize and form a gel between the platelets, around the platelets, and gives more mechanical strength to the forming clot. Okay, so platelet aggregation, coagulation, enzyme reactions, fibrin polymerization are the three big parts. Okay, I don't know if I need to do this, but I'm going to. Fluid dynamics plays a big role because the blood is flowing. And so in some of the models, you'll see a lot of PDEs from fluid dynamics, more complicated than what I'm going to briefly tell you about. Oh, I think I went too far. Tell you about now, but I thought I'd warm you up. And some of the modeling, the fluid dynamics is there, but very much simplified. So fluid mechanics is a part of continuum mechanics. It's still ruled by Newton's laws, okay, but they're in a form that applies to chunks of material. And Newton's second law says the time rate of change of the momentum of a chunk of material is equal to the total forces acting on it. And those forces could be so-called body forces acting on points in the fluid chunk, and surface forces acting on the surface, forces that are exerted by the surrounding fluid on that. It's convenient and common to describe surface forces in terms of a stress tensor, which you can think of as a matrix. The surface force on a point between two chunks of fluid is given by the stress tensor dot the normal vector at that surface pointing into the outside fluid. Okay, you plug that in instead of this sigma dot n. You use the divergence theorem and the arbitrariness of this region, and you get a PDE that looks like this. Nothing has been said so far about what sigma is, okay? If we're talking about an ordinary fluid like water, the model is that sigma has two components, a pressure contribution that's isotropic, this is the identity tensor, and a viscous part that involves gradients of the velocity vector. And if you plug that in, you get the Navier-Stokes equations, which are widely studied for simple fluids. Okay, so diagrammatically, the two kinds of forces that are taken into account in a simple fluid are pressure. The outside fluid pushes on the chunk, and viscous stresses, which is friction. If the outside fluid is moving at a different speed than a fluid chunk, then they rub on each other and exert forces. The other critical thing to understand about fluids, at least viscous fluids, what we're talking about, is the no-slip boundary condition. At a fluid-solid boundary, the no-slip condition says the fluid velocity must match the velocity of the solid, often it's stationary, at the adjacent point. And for a simple fluid, these forces, incompressibility, which I forgot to mention, which is that for water, it's very hard to compress it, so it's treated as an incompressible fluid. And in fact, that determines what the pressure is. Forces, incompressibility, and these boundary conditions determine the fluid motion. Okay, what do you really need to know? Okay, blood clotting happens in pipes. Our vessels, we can think of as flow through a pipe. You have pressure-driven flow through a pipe with a higher pressure at the left than at the right. Unless there's some other disturbance, you get a parabolic velocity profile, which is indicated here. The fastest flow being in the middle, and the flow being zero at the walls of the tube, assuming the tube is stationary. That means there's a velocity gradient everywhere, but in particular at the wall. And if U is the velocity component in the downstream direction, and Y is this direction, we're particularly interested in the derivative of the downstream velocity, the tangential velocity, as you move away from the wall. And that's called the shear rate. It has units of 1/time. Why is it so important? Okay, well, okay. It's very important in platelet deposition for a whole host of reasons. One, the near wall velocity within a short distance of the wall is equal to the shear rate times how far you are from the wall to first order. So higher shear rate means higher near wall velocity. Transport of cells like platelets and proteins to the injury and out of the injury, away from the injury, would therefore be proportional to the shear rate because they depend on the velocity near the wall. The faster the flow, the shorter the time a protein or a cell spends passing over the injured part of the vessel. And so it has to react more quickly. So there's a time scale for reaction that's proportional to 1 over the shear rate. And then the viscous forces that I mentioned previously, the sliding friction forces, is proportional to the shear rate according to the model used for simple fluids. So a lot of things. That means the forces applied to platelets that are trying to cling to the wall will have components that are proportional to the shear rate. So the shear rate is very important. It determines transport and forces and time in which things can react. Okay. One slide on the basics you need for understanding the first part of the talk. Platelets aggregate. Okay, as I already mentioned, platelets surfaces display a whole host of receptors. Some of them, many of them, are critical for platelet adhesion to the vessel wall when it's injured, or cohesion between platelets. Okay, so this is adhesion to the wall. Some of the receptors bind to collagen exposed when the vessel is injured. Okay, but for cohesion between two platelets, it's a more complicated process. Receptors on two different platelets have to bind to the same bridging molecule. So either fibrinogen, it binds to a certain kind of receptor on the platelet, and then forms a little spring. That's how we're going to think of it. Or a von Willebrand factor, another protein that's in the plasma, can bind either to the same two receptors or to a different kind of receptor. But there's two receptors, they have to be joined by something that's in the blood plasma all the time. So think of it as bridging. Now there are lots and lots of these kinds of receptors, the ones I've drawn up here. There are 80,000 of these on the surface of a platelet. I should give you some idea. A platelet's about 2 microns in diameter and long, It's discoidal, plate-like. It's about 2 to 3 microns in that direction, about a half a micron in that direction. So they're small, yet they have 80,000 of these receptors. This kind, called alpha 2b beta 3. They're so-called integrin receptors. And it's important that in resting platelets, they're in a low affinity state. They're not really capable of binding fibrinogen or VWF. They need to be activated first. There's another large class of, a large group of receptors of another kind, glycoprotein 1b. There are about 25,000 of those. They're always ready to bind. On the resting platelet that's circulating, these guys are ready. Okay? They bind to this protein VWF. What keeps them from binding all the time? The VWF has to be activated in some way in order to allow it to be the bridging molecule. Okay? So through these different kinds through these different bridging molecules binding to receptors on 2 different surfaces, we create molecular links, molecular springs between the 2 surfaces. Imagine you wanted to model this, and one possibility is, as Thomas mentioned, I am also a Peskin student. The immersed boundary method is part of my genetics. One possibility is to say, I'm going to model discrete platelets interacting with the fluid, modeling each of them as some deformable object. The platelets might be in different states, resting or activated. There might be additionally chemicals that can activate the platelets. And we can follow the motion of the platelets, and under certain circumstances, we can allow them to form bonds between one another, mimicking the molecular bonds. Okay? We've done some of that, as indicated by the picture, but this approach is only appropriate for very small vessels where it's feasible to follow the individual platelets that are in that small vessel. For large vessels like the coronary arteries, it's just unfeasible. It's not the way to go. Okay, but the coronary arteries are a place where clotting can go very wrong. And it can go very wrong if the person has coronary artery disease. Coronary artery disease is connected with atherosclerosis, which results in the plaque growing slowly into the vessel lumen over many years, perhaps. That plaque is a mixture of cells, fats, disorganized proteins, and things. It's fragile. Okay, so things can happen to it. The surface of it can be eroded, and then that provides signals for platelets and other parts of the clotting system to start, and you can get a clot forming on it. Or the plaque could actually split open, completely rupture, exposing a lot of clot-promoting materials. Okay, and 2 consequences of that are bad. Pretty much okay. You can have a clot form, but it's not strong enough, and pieces of it break away and flow downstream. That's called embolization. It doesn't block this vessel, but it could be blocking things downstream if these chunks are big and too big to go through the downstream vessels. The other possibility is the formation of an occluding thrombus, something that blocks the vessel. The plaque took years to form. If it fractures, if it ruptures, and a clot forms, that could happen in an hour or so. Okay. So we would like to have models to look at coronary arterial thrombosis in general, but with the picture I just described in mind. But a challenge is that there are at least 2 spatial scales. The vessels are millimeter in size, diameter. Platelets are micron in size. The effect of the platelet aggregate on the flow through the vessel, it happens at a millimeter scale, but things that are happening between the platelets, the bond formation, which is happening at a micron scale, certainly affects the strength of this, affects how close the platelets are within this, which means it affects could be porous, affects the porosity. So microscopic scale, micron scale things affect the macro scale. Okay. We don't want to track both of them. Okay. So I'm going to describe a macro scale model, but it was derived from looking at things with two scales. And I'll allude to that once somewhere in the talk. Okay. But we're able to upscale the stuff from the micron scale to get effective effects at the macro scale. So this two-scale model tracks through using distribution functions the platelet bonds that we would track individually in a discrete model. And from that distribution of bonds, it defines, we calculate stresses due to the bonds which affect the fluid. So the bonds are going to give rise to another contribution to a stress tensor. So from the two-scale model, which has things at both scales and has a PD which will briefly make an appearance for the distribution of bonds, as I said, we can upscale, we can derive equations for the evolving bond stress and the bond concentration at the macro scale, which captures many of the features at the micro scale. And we've done this for a lot of years with a different succession of models. The original one was single phase, by which I mean the fluid and all of the platelets move at the same velocity. That model had some successes. It could produce occlusive thrombi. They could block off a whole vessel. Or, under different circumstances, a clot could form and then break away. So capturing the two basic kinds of behavior. But it had serious limitations. Because of the single phase assumption, for a thrombus to form in this model, it had to form very, very quickly. Otherwise, let's just leave it at that. Because of the single phase assumption, the only mechanism for increasing the density of platelets in some region was diffusion, not advection. And so in the model, the density of platelets in the thrombus hardly surpassed the background density in the bulk blood. In a real thrombus, the density of platelets in the clump can be 100 or 200 times the density. I mean, when I say density, I mean number density. Sorry, you can think concentration. Number density, number per unit volume, can be 100 to 200 times what it is in the bulk. So the conclusion is it's critical to have relative motion between the bound platelets in the thrombus and the rest of the material. And the rest of the material will still treat as moving in at a single velocity. That'll be true for the fluid and for single unbound platelets in the blood. So sort of the picture is early on in clot development, platelets, there are a few platelets, they're linked together, there's gaps between them, there are relatively few bonds between the platelets, so they can only sustain small forces on them. But it's very porous because there's lots of gaps. There's some drag of the fluid, and that brings fluid and platelets into proximity. Advection brings fluid and platelets into proximity with the already bound ones. Okay. Later on, after the clot has built up, platelets have built up more, their density is higher. They provide more of an obstacle to the flow, causing the flow to divert around. And they've had time to form a lot of bonds between one another and to be strong enough to withstand the drag forces. We want a model that can capture that kind of picture.
And so, Aaron, from that picture, it's kind of, I think I understand why in this porous case, the thrombus is going to form more slowly because now some of these clotting factors can be advected away. But then what about this? Like, how does this explain the higher density one?
No, I mean, no, I mean, you're right. Things get washed away. Things produced there get washed away. But it also brings more things in from upstream. If this fluid flow through the aggregate, more platelets are advected into proximity with the aggregate, okay, where they can attach, increasing the density of bound platelets. More platelets will come in. It's sort of like think of a sieve, right? Things can attach to our filter. You know, if you're waiting for things to diffuse to it, stuff is going to accumulate slowly. But if flow can carry the particles through it, there's a chance for them to bind much more rapidly and densely. That's what this picture is about. You are absolutely right that, you know, flow through it has another effect, which is to wash away things like signaling molecules and things. So it goes both ways. It's hard to predict a priori what increased flow will do. Okay? But so in this model, the clot will be a material consisting of bound platelets that grows in extent. It grows in number density. It's got viscoelastic properties because of the bonds, and it's porous with a porosity that is less the greater the density of platelets in the thrombus. So the viscoelastic properties and the porosity of the thrombus evolve as platelets deposit. Okay, so the current version of the model it's a spatial temporal model. It treats 4 populations of platelets, 2 of them moving around as single platelets in the fluid. One of those is unactivated, so unactivated fluid phase, and activated fluid phase. And then there are 2 populations of bound platelets, unactivated bound platelets, and activated bound platelets. The fluid and the 2 types of fluid phase platelets move with the fluid velocity u sub f. The bound platelets move at a different velocity, u sub b for bound. And so these can be different from one another. Okay. The form of the model is a so-called mixture model. Platelets and bound platelets and fluid can coexist at a given location. How much of each is there is indicated by their respective volume fractions. The volume fraction of fluids and individual platelets is theta F. The volume fraction of bound platelets is theta B. Those 2 things have to add up to 1. Other processes in the model is unactivated platelets can be activated by different mechanisms in different contexts. We allow for 2 types of platelet bonds to form and to break. The platelet bond forces need to resist the drag force that the fluid is exerting on the bound platelets. Otherwise, the clot breaks up. And some parts of this model are standard advection, diffusion, reaction kinds of things, but the treatment of the bonds and the stresses they engender was the most novel part. And why didn't that work? Good. So there are mechanical parts of the model having to do with the stresses in the fluid dynamics. Okay? I should say this model is mechanics heavy and chemistry very, very light. There's no coagulation in this model yet. Okay? So there are 2 Navier-Stokes-like momentum equations, one for the fluid phase velocity, one for the bound platelet velocity. Okay, they each pressure, they have viscous contributions like a simple Navier-Stokes. They have a drag term which is proportional to the difference in their velocities at a particular location. And this also has a coefficient that increases sharply as the density of platelets in the thrombus grows. So as the thrombus, as this mass has a higher and higher density of solid platelets, theta B goes up, C of theta B goes up. And it's given by this semi-empirical function. Okay. For the so that's all that's happening for the fluid. For the bound platelets, there's the additional effect of the bond forces. And I can't see my slide because you got these pictures in front of you. There should be a divergence of sigma B somewhere over on the right. And so we capture the bonds through another stress tensor.
Yeah, the divergence is there.
Okay. It's in addition to the viscous one that's in a simple fluid.
Yeah.
And it's trying to, and it's how the bonds manifest their effect on this fluid. They act directly on the bound platelet fluid, not on this fluid, but their effect is transmitted to the other fluid because these two motions are coupled by the drag. The motions are also coupled in one other way. The mixture of the two materials has to be incompressible. All of space is occupied by platelets or fluid. Okay, so we call this an co-incompressibility condition. Neither velocity field by itself needs to be incompressible. It is if only one material is at that point. But if there's a mixture, neither needs to be incompressible, and one fluid can move into a region by expelling the other. Okay, so then the other critical part of is describing the bonds and the bond stresses. And Z is the concentration, the number per unit volume of bonds between platelets at a location. They're attached to bound platelets, so they move at the bound platelet velocity. This equation accounts for formation of new bonds. There are different rules for how bonds can form between different platelets in different states, so I'm leaving this kind of vague, but bonds can form, and then bonds can break. Okay, so the Z will go down if bonds break. This breaking rate in reality, is a function of the force on the bonds, which you can think of as a function of how stretched each of the bonds is. And in the model, we don't have individual information about how stretched the bonds is, but we have a surrogate for that. We have a measure, an estimate, an approximation to the average bond length connecting platelets at a point to nearby platelets. And that's what this indicates. Okay, so bonds do that. The stresses they create, the stresses that are created by the bonds, well, there's a stress creation term. This function is proportional to that one. Stresses are created by the bonds in an isotropic way. When the bonds break, the stresses relax. Okay, but then there's these other terms. This is simple convection at, okay, but these are terms that arise in the derivation because the two ends of the bond are not at exactly the same location. And so if there's a gradient in the velocity, it can stretch and change the orientation of the bonds. And that's what this term captures. This whole thing here is something called the upper convected Maxwell derivative, and it's common in complex fluids for polymers and things like that. It showed up, we didn't know that when we derived this, but originally, but it showed up in this model pretty much for the same reasons. You're talking about motion of things that have a finite length. Okay, I think I'm going to skip this. For the two-scale model, there was another function. No, I better say something. There was a function E, the elastic link density, and it's got this interpretation that if you look at a small region around the point X and a small region near X, and you count the platelets, count the bonds between platelets in those two regions, that is intended to be given by E of these two spatial variables, which tell where the two regions are, dx, dy. These are two volume elements. E is numbered per volume per volume. And in a variety of ways, which I'm not going to, we can derive, taking into account a variety of things, we derived a PDE for E, which allowed for creation of bonds in a way that depends on how far apart the platelets are, breaking of bonds, depending on how long they are. That's the two-scale model. We wanted to get rid of the microscale, the Y scale. And from E, we defined the two variables related to bonds that were on the previous page. This is the concentration of bonds. You get it by looking at platelets at X and integrating over all of the bonds connecting platelets there to platelets anywhere. Okay. And the stresses, similarly, each bond contributes a certain amount to the stress, 1/2 the stiffness times YY transpose, and you add them up, multiplying by the distribution of them to get the total stress. Okay. In the model, the macroscopic effect of the bonds is through these guys. We started with an equation for E. We derived equations, or at least approximate equations, for this and this by taking the time derivative, say, of Z, get E sub t in here, and then using that equation and some manipulations afterwards, integration by parts and a variety of things, to end up with an equation for Z. You don't get an exact equation. You have to make some approximation. And the approximation is to assume that beta, the breaking rate, depends not on the individual bond lengths, but on the local average bond length, this thing. Okay. So we do that for that. We do a similar thing to get an evolution equation for the stress tensor, and that's what we saw on the previous page. There are equations for them. I didn't put them on here. Did I? Wow. Oh, there they are. Did I skip this? I think I did. I think I skipped this. Sorry. There are equations. These are the more standard parts of the model. Equations for how the 4 number densities of the different populations behave. The fluid phase ones advect with the fluid velocity. They diffuse. Really, it's not diffusion. They're being jostled by red blood cells, stirring up the local motion. And they can transition between states. Unactivated fluid phase ones could be activated to activated fluid phase ones, moving from this population into that one. Fluid phase guys can bind and be removed from the fluid phase, or platelets that are bound can unbind. So there are transitions between them. And to explain the model in full, I'd have to tell you what those are, but I'm not going to do that. Okay. I said this is chemistry light. There's a single chemical in the model. Platelets, when they are activated, release a bolus of chemical. Think of it as adenosine diphosphate, ADP. It's one of the signaling molecules. And so the rate of secretion of that is that bolus size times the rate of activation of platelets, their motion from U to A, whether they're in fluid or bound. Okay. And the volume fraction, which appeared on the next page in the mechanics equation, is not tracked independently. It's related to the bound platelet number density. You take those number densities, you multiply it by the size of an individual platelet, and you get the volume fraction occupied by them. And the fluid volume fraction is just 1 minus that.
And Aaron, in the evolution equations for the bond concentration and bond stress, this average bond length appears in the evolution. So then is the average bond length somehow can be written in terms of the other variables?
Yes. Okay. The average squared bond length can be expressed as, I don't think I put it down, as the trace of sigma divided by Z. Okay, you'd have to look at, when you take the trace up here, you're going to get mod y squared appearing. So that's right. So if s is a constant, bring that out. So you get something that looks like the second moment of y. Okay. Z divided by z means you're dividing by the probability function e, the distribution function. So that gives you the average of the squared length. Taking the square root of that is what we do as a proxy for the average length. We've compared it with some simulations of the full 2-scale model, and at least under, it has reasonable agreement, but it's a lot less expensive. Okay, I'm talking too slow. The model involves modes of activation by contact with the injury, exposure to the activating chemical, and in some versions, through signals transduced through the cohesive bonds that they're joining the platelets together. They not only hold things together, but there's more and more evidence that when there's force on those bonds, there's a signal to inside of the platelet, which cause some of the reactions leading to activation. Bond formation can't happen unless there are platelet surface receptors locally able to form the bonds. Okay. For one kind of receptor, the GP1B, if there are platelets locally, there are receptors locally. For the other kind of receptor, the integrin ones, the platelet has to be activated before those receptors become available. For bond formation, you also need the corresponding bridging molecules to be in the fluid near the platelets. We are extending the model to include explicitly concentrations of those, but right now we don't track those individually. Some signal, one of these, must turn on the response. Okay. Again, I can't see what's written here. Can I move this? I should be able to, right? Yes. Okay, the bonds, you needed to be able to turn on the ability of some of the bonds at least to form. They break at a rate that's proportional, that's sensitive to the force on them. For one kind of bond, so-called slip bonds, the breaking rate, according to Bell's model of such bonds, the breaking rate increases exponentially with force. That's true for one of the types of bonds in the model. The other type of bond has been shown to have a different behavior, so-called catch-slip bonds. If you apply moderate force to the bond, you actually decrease the rate of breaking. When you apply larger forces, you increase the rate of breaking. So there's a minimum rate of breaking at some moderate force, and that can be influential. If the force on those bonds is in that range, they last longer. Okay. So we've done a bunch of things. I'm just going to describe a couple of experiments. So looked at flow in a rectangular channel. Imagine that a little region over here is injured, meaning that platelets that come into that region can bind and become activated. Okay. The situation is that this is a moderately high shear rate for the vasculature, that's sort of middle of the range. The Reynolds number is significant, so inertial effects matter. And we're using, to the extent we can, physiologically based parameters for the bond formation and breaking rates and their strength parameters. Don't have perfect information, but it's a lot better than what we used to do. And here I'm showing two different experiments. Our collaborator, David Koo, formed clots under arterial flow conditions and then measured the permeability of fluid through those clots. Okay. That permeability can be used to inform the coefficient in front of the drag term. High permeability meant a relatively low coefficient. Low permeability means a relatively high coefficient. And so here we have low drag coefficient, lower drag and higher drag, informed by these measurements. And so the range that he was able to see. For the lower drag, in this case, this is the situation after 100 seconds. This was the region where things could start. You got buildup of, this is the density of activated bound platelets, the number density. Its color bar is here. A unit of, if it had a value of 1, that would be the background concentration of the platelets, background number density. You can see that it reaches well over 100, at least in here. This is the fluid velocity. The fluid, this by this time, this is very impermeable, and most of the flow goes around it. So here we have the buildup of a thrombus on a physiological time scale and with high density regions. This is this, okay, let's leave that. This is set up in exactly the same way, except the resistance to the drag, that coefficient was set to the high end of what was measured experimentally. It's about 20 times higher. And what happens is a clot does not survive. Things bind, but then the bonds subject to a higher force break. Things embolize and chunks of the clot move downstream. The scale, and I put this back, the scale up here goes from 0 to 1 to 6. So even at a red region over here, which there's none, would be much, much less dense in terms of number density of platelets than over here. So there's to build a stable clot, if that's your goal, there are design constraints on relating to permeability, the rate of formation of bonds, their stiffnesses, their ability to withstand forces, and their breaking. And this is an indication of one of those. The higher drag, the bonds in these simulations did not form rapidly enough for this clot over here to remain intact. And what you can see from these heat maps, this is the breaking rate function, and its base rate is 0.06 before it does the exponential increase. And in this simulation, it never got much above that. This is 0.063. So a little bit of force-induced increase in breaking. But over here, the forces were bigger because the drag is higher, and the breaking rate reached as high as 60 times the base. No, it's not 60 times. 0.06 to 60, 1,000 times what's over here. So the forces were bigger, the bonds broke more rapidly, and the thing couldn't hold together. You know, I'm supposed to stop soon, so I'm going to skip the rest of this part and tell you a different, no, I can't do that. I do have to stop in, it's like 7 minutes, right? Something like that. Okay.
Yes.
Let me just go on and pretend I'm going to tell you all about the rest, but I probably won't. The other half of the talk is looking at coagulation plus platelet deposition under flow. Now, we just treated the platelets in a very complicated way, and we treated the flow in a complicated way. In these models, we opt to treat the platelets and the flow in a simple, much, much, much simpler way, but to treat the chemistry in a much more comprehensive way. So this is a picture of most of the reactions involved in the coagulation enzyme cascade. And our model has almost all of them. It doesn't have this final step of polymerization, but it has all of these in it, okay? Some of the key things about this, okay? Most of the enzyme reactions in this system are so-called protease reactions. An enzyme cuts off a piece of another protein. Okay. Typically in the system, what this enzyme is doing, it's cutting off a piece of its substrate Okay, and by cutting that off, it's converted that substrate into an active enzyme of a different type. Okay, a word that's used in the field for the precursor to the enzyme, the thing that's not been activated yet, is a zymogen. So each enzyme typically converts a zymogen into the corresponding enzyme. Okay, enzymes also do the similar kind of thing to a molecule which isn't an enzyme, but serves to help enzymes work more efficiently. And those are so-called cofactors. So we have inactive cofactors in the plasma. By enzymatic action, they can be converted to active cofactors. They then combine with a certain enzyme to form enzyme complexes. Critically, these complexes happen on surfaces. The first surface for one of them is the subendothelium, the injured vessel wall. Products that are produced by that, if they make their way to the surface of activated platelet, form two sequential other complexes. And after all of that, this guy produces the critical enzyme from it. So I was just going to walk you through this diagram. So things start out down on the subendothelium. When the injury causes a molecule called tissue factor to be exposed, molecule called factor 7A, F7A, from the fluid binds to it, and this becomes a very powerful enzyme complex. It activates two other proteins. It takes protein zymogen. Most of the proteins have Roman numeral names. Factor 10 and converts it into activated enzyme 10A, and 9 into active enzyme 9A. 10A and 9A are weak enzymes on their own. But if they make their way to the surface of an activated platelet, which they're not guaranteed to do, because to do so, they have to go out into the fluid phase and the subject getting washed away. But if they make it, the 10A activates a cofactor molecule 8 to 8A, and the 9A binding to the platelet binds to the 8A, and they form a second powerful complex. Okay, it's called 10ACE because it is going to activate 10 to 10A. This did that too, but this is doing it on a different surface. It's doing it on the platelet surface. And location matters because this guy doesn't have to go out into the fluid before doing the next thing it's going to do. Okay, what it does, it activates another cofactor for itself, 5 to 5A, and then it forms another complex, a third complex of 5A and 10A, and that's the thing that takes the precursor to thrombin and converts it into thrombin. Okay, so we have three complexes. There's a lot of other stuff going on, but products of this complex, if they can make it to the platelet surface, are responsible for this guy forming. Product of this guy can make the pieces that are needed to form this complex. Okay. So there are three complexes. That gives the potential for tremendous amplification of the signal, since each of these is producing things at a rapid rate. Once thrombin exists, it feeds back in numerous ways to speed its own production. And so another positive thing that can cause tremendous response. So I meant to mention the word switch all over the place, but the clotting system needs to be able to be turned on fast so we don't bleed to death. Okay, but it needs to be safely off when you don't want it. So amplification and positive feedback are important for the rapid response. There are multiple chemical inhibitors that slow it down or inactivate it. And other things that keep it from happening are that some of the important components, like tissue factors, not normally exposed to the blood. Okay. Okay, so we modeled this, we have spatial temporal models of this too, but the model that's been the most influential because we can do many, many calculations with it because it's really cheap to simulate, looks at these events in a small reaction zone above a small injury. And the simplifying assumption is that each species in here is well mixed. It's distributed, even despite the way the picture looks, the platelets are distributed in this little box. Each of the proteins is distributed uniformly in it. So each is described by a concentration or number density that depends only on time. So the model has ODEs. All of the reactions are treated by mass action kinetics, even the enzyme reactions. And I can discuss that later for anyone who wants. Okay. Proteins are distinguished by whether they're in the fluid phase or they're bound to platelets. A difference between those is that flow and diffusion can carry fluid phase proteins as well as fluid phase platelets into this reaction zone from upstream or out of it downstream. And in this simple model, we have an effective mass transfer coefficient. It's just a rate reflecting the local shear rate and the diffusion of the species involved. But so that's how flow enters here. It just stuff can come in, stuff can go out. No treatment of forces like in the previous model. Platelets in this model can be activated. Platelets can bind to the subendothelium and to one another. Each activated platelet has a specified number of binding sites for different coagulation proteins. You need those binding sites in order to be able to form these complexes on the platelet surface. So a second regulator of the whole thing is the availability of activated platelet surface, which, as the platelets accumulate, you get more and more of that surface. But other things can prevent that, can limit how much accumulates. The zymogens and the inactive cofactors must be activated before forming complexes. Okay, the picture I showed you is our version of stuff from medical textbooks, all the reactions. Okay, what those don't include are two, and so there are multiple chemical inhibitors to regulate the reactions. What's not included in the textbooks are two major physical inhibitors. One has been alluded to already, it's flow. Enzymes produced locally that are in the fluid can get washed away, therefore reducing their concentration locally very much. Flow is a major inhibitor of what's happening locally. The other one, we postulated, there's some experimental support that it was a good postulate, is that platelets are attaching to the surface, okay? As they attach to the surface, they're covering part of it. And so they physically, by blocking, inhibit activity of enzymes on that surface, tissue factor 7A. Okay? Without that additional kind of physical inhibition by platelet deposition, there are things that we should have been able to capture with the model, but we weren't able to. And we could explain why not, why what people thought in their thought processes happened weren't happening here. And the answer to that was flow. Most everybody studies these things in static conditions. Okay. So we posited this physical inhibition and added that to the model. I'm going to show you two slides of classic results and one slide of recent results. Okay. Inputs to the simulations, we specify the inactive protein and platelet concentrations. We specify the flow speed. Of course, we specify the kinetic parameters. And we specify the level of TF exposure, that is the density on the patch of injured tissue is specified, low density, medium density, high density. The model outputs are concentrations of all of the proteins and platelets treated in the model. In the current version of the model, there are about 130 of them. Okay. Thrombin is an end product, but there are many, many intermediate species on the way to producing thrombin and regulating it. The individual proteins and complexes of proteins, et cetera. We got all of those. So here's a set of results of a set of simulations which indicate TF, the exposure of TF acts in a switch-like way. Doing a series of simulations in which we gradually increase the density of tissue factor that was imagined to be on the surface, and then looking at the results of the simulation encapsulated by looking at thrombin 10 minutes after things began. That's what's plotted here. Look at the blue curve. That's at a low shear rate. For tissue factor, and a physiologically meaningful level of thrombin is 1 nanomolar, 10 nanomolar, or 100 nanomolar. And this is a log scale. So things down here don't matter. There's essentially no production of thrombin until you get to a tissue factor like this, and then increasing the tissue factor a little bit causes a tremendous change in the thrombin production. So tissue factor, availability of tissue factor is a switch. I mean, this is the prediction of the model. Okay. We think we're the first ones to make this proposal. There's some controversy about that, but a number of years, but there was no way of testing this under this situation until a number of years later, a group built, inspired by our predictions, built laboratory devices where they could look at platelet coagulation under flow and measure thrombin. Up until then, people hadn't done that, and threshold behavior was definitely seen. The threshold changes with the shear rate because it's easier to wash stuff away at the higher shear rate, but it's a weak dependence. And I'm not going to explain it, but in the model, the existence of this threshold depends critically on the effects of flow and on platelet coverage of the subendothelium. We could also look at various disorders. Hemophilia is a deficiency of one or another of the coagulation proteins. Hemophilia A, which is the common one, deficiency of this molecule, which is the precursor to the cofactor for this complex on the platelet. Hemophilia B is a deficiency of the zymogen, which is the precursor for that enzyme that forms part of that enzyme complex. Either of these are deficient, severely deficient, you get much less of this. That is what produces factor 10A enzyme on the platelet. That's reduced, you get less of the final complex, and therefore less activation of prothrombin to thrombin. The model can capture that kind of things. In fact, it captures the much reduced thrombin for both of them and the greater reduction in thrombin for hemophilia A than B. It can also capture what happens if you have lower platelet count, but let's skip that. Final thing, this is one of our coolest results. So I really do want to explain it, even if I've already talked too long. It's observed that persons with hemophilia A, a deficiency in that precursor to the cofactor, that is deficiency in factor 8, they can have less than 1% of it. They exhibit a wide range of bleeding tendencies. Okay, they're not producing enough thrombin, as much thrombin, so they can't produce clots that are as effective. They bleed, but some of them bleed spontaneously. Others need stimulus to bleed. A longstanding question is, why this range of tendencies for comparable levels of deficiency in this protein? And people have been wanting to identify so-called modifiers of hemophilia that could explain why some people don't bleed and other ones do. So they're looking at other conditions in the blood, protein levels, other things. Okay, and you can imagine doing that experimentally. Conceptually, if you could find enough patients and you look at their concentrations of other things, including platelets and proteins, you could try to correlate those other levels with their bleeding tendency. Can't do that. There are far too few hemophilia patients. It's far too expensive to run all those tests, and there are far too many candidate modifiers. So that's infeasible. So what we did is look at one set of candidates, which is the concentration of the other clotting proteins besides the deficient one in the blood plasma. And the justification for doing this is that protein levels and clotting things, even in normal healthy people, are seen to vary plus or minus 50% from some baseline level. So we took the model, we set the factor VIII concentration, the thing that's deficient in hemophilia A, to 1% of its value. And we did a couple 100,000 simulations where we randomly sampled the other factor levels between 50% and 150% of baseline and saw what we got. In a sense, we're generating synthetic patient data because we're looking at people with different levels of the other coagulation factors and seeing how much thrombin they produce. For most of those variations, you got very little thrombin production, below 1 nanomolar. But there was a subset of them which you produced 10 or even 50 nanomolars of thrombin. We looked at those simulations. We looked at the distribution of the protein levels, not for all of the simulations, they were random and uniform, but the distribution of protein levels in the guys that produced a lot of thrombin. And this is what we saw. This is baseline level, plus 50% and minus 50%. Most of the things we looked at were pretty much distributed equally above and below 100% and near 100%. Two species were very, very skewed. Factor two is another name for prothrombin. This is the precursor for the final enzyme thrombin. It was high, closer to the 150%. And factor 5, which is precursor to one of the cofactors, was low, close to 50% in these in the simulations of hemophilia that still produce substantial thrombin. Now, that's what the model predicts, but oh God, this is counterintuitive. Factor 5 is the precursor for factor 5A, which is the cofactor in the final critical enzyme complex that produces thrombin. Low factor 5 should hurt thrombin production. Further, there is no direct interaction anywhere in the system between the factor 8, the deficient guy, and factor 5. So what's going on? The model predicted this. I should say our group's experiments confirmed that low factor 5 does help produce more. If you lower the factor 5 in someone with hemophilia, in the blood of someone with hemophilia, in a laboratory experiment, you get more thrombin than with higher factor 5. So the prediction was seen experimentally, was tested, and the prediction was seen to happen. So what could be going on? Well, the model, besides being able to make predictions, you can go back and look at all the intermediates that get you to the final result. And we saw what the mechanism is. This is the mechanism in the model. It doesn't say it's the mechanism behind the real observations. That's something we're still looking at. Okay, but in the model, the reason low factor 5 helps with hemophilia A is substrate competition. On the platelet surface, 10A that is bound to the platelet surface has several roles, one of which is to activate factor 8 to 8A to form the 10-ACE complex. Another is to activate factor 5 to 5A to play a role in the prothrombinase complex. So here's a molecule 10A. It's torn between which of these it's going to do. Typically, there's a lot of this. In hemophilia, there's very little of that. Reducing the factor V to 50% allowed more of this to work on the little factor VIII that was around, activating it and producing more of this than might be expected. So by reducing substrate competition, the model produces more 10-ACE. You do need 5A in the end. If you reduce the factor V concentration to 1% of normal, that's bad. But there's sufficient, at 50%, it's sufficient to form all of the prothrombinase you need. What we saw was low factor V, low normal factor V, is critical to turn on this greater thrombin production. It's sort of like a match to ignite a flame. To get high thrombin production after that match, you also need high normal prothrombin. So quantitative modeling is necessary to inform our thinking about these kinds of systems. Considering platelets, which have both procoagulant roles and anticoagulant roles, is critical. Regulation involves not only the chemical reactions that people long talk about, but physical processes. The model can make testable predictions and can make, in some cases, surprising but testable predictions about how when you perturb the system in multiple ways, what happens after you perturb the system in multiple ways. And with that, I will finally shut up.
Thank you, Aaron.
Okay.
Thank you.
Sorry.
Yeah, thank you.
Okay. So now you have a very long talk. But if you have questions, I have a little time before I have to run off to teach. I am sorry. It went 17 minutes long.
I have a very short one. So you mentioned if there is no flow, then the threshold, you won't have the threshold. Is that right?
You wouldn't have in our model, the reason for the sharp threshold has to do with flow. Okay. How do I say this? But in the model, flow also reduces the effectiveness of some of the chemical inhibitors for reasons like it washes some of things away.
Mm-hmm.
In an experiment, in a static situation without flow, you won't have a threshold because of our mechanism, but you could possibly have it because the inhibitors that under flow don't matter much in static conditions might matter, and they have to be overcome. So you can have a threshold for a different reason. So I mean, you have a threshold if you have some nonlinear positive feedback and overcoming some hurdle, right? Some obstacle. The obstacle in our flow simulations involves flow and not chemical inhibitors. In experiments under no flow conditions, it's possible that those chemical inhibitors are the things that have to be overcome. And so these aren't contradictory. It's just in different situations, things are different. People talk about overcoming the chemical inhibition, as necessary to get a strong response. People hadn't been talking about overcoming physical processes that flow, that are covering the wall as something that maybe in vivo you really need to take a treatment. So you can get thresholds in static things, but for different reasons.
Mm-hmm.
I would argue, we're clotting under flow in our bodies. So our goal is always to try to say something about a more in vivo situation. Does that help?
Yeah, thank you.
Anybody else?
Very, very quick and basic question.
Oh, sure.
How fast and slow is the blood flow rate? Like
It
in
depends.
the thinnest blood vessel and the biggest blood vessel should be really different.
Yes. But as I argued, the really critical thing is not the overall flow rate, it's the shear rate.
Right.
Okay. And so that's affected both by the speed of flow and by the diameter.
Right.
Okay. So the shear rate is actually highest in very small arteries called arterioles. Those are just upstream of capillaries. Capillaries are very, very tiny, and it's where the oxygen gets, where oxygen goes from the red blood cells to the tissues. Just upstream of that are small vessels, about 50 to 100 microns in diameter of arterioles, and the shear rates are highest there, 1,500 per second, 2,000 per second. And big arteries, more like 500 per second. Big veins, more like 100 per second. Veins have, because the flow is less rapid than in the arteries, because the pressure differences are smaller once you get past the capillary, and because the big veins are big diameter, the shear rates there are relatively low. The clotting system, I can say this, responds in the coagulation versus platelets versus how much of each goes into forming a clot varies depending on your shear conditions. And part of it we can explain. Part of it still needs to be explained. Anyway, there's a wide range of shear rates from about 50 inverse seconds to a couple thousand in healthy people. In people with a narrowed coronary artery because of plaque, the shear rate is significantly higher, multiple thousands. And if you actually cut a vessel, so blood is flowing out rapidly into a very low pressure thing, you can also get very high shear rates there. So it, in some ways, should be mysterious why clots are even able to form under very high shear in partially constricted coronary arteries. I think the answer is because you need to be able to form clots when a vessel is cut and not flow, and it's a high shear situation. So the ability to block, to seal off a cut if it's not too big, probably is in a sense an underlying reason we have problems in our coronary arteries and their high shear. Under shears that are much higher than would normally be in the body that's not cut and is healthy. I don't know if I've answered your question. I'm rambling all over the place.
That's what I was kind of wondering. Thank you.
Oh,
If we don't have more questions, let's thank Aaron again.
Yeah.
Yeah.
You-
yeah, thank you.
Nice to meet two of you and to see you again. And it's nice to see my classmate from Wesleyan. I haven't seen him since 1977. Danny Ruberman, the topologist. And Thomas, of course. Okay. Hope to see you again soon.
Yeah. Bye.
Yeah. Bye. Thank you.
Bye. See you. Okay. Where's the